So, anybody has a question regarding the code? Were you able to, I mean, there is an assignment anyway, and I hope the code helps in working on your assignments. I'm just gonna go and highlight like the main functions in here. Basically, tune is a really good function that you can use with not just SVM. You can use it with any other algorithm to do cross validation. Pretty much is for tuning the parameters using cross validation, and that's mainly how we tune the parameters. So basically, in here, you need to put the list of the list in here, the values that you want to try. So in this case, since we're working with SVM, we have a C, the parameter C, which is the cost, and you want to try different values. So tune function here will run your SVM model for number of experiments, depends on how many values you set in here, and it will do tenfold cross validation. So it will choose the first value of C, this one in here, and run tenfold cross validation and report the result, and then try this new value, tenfold cross validation, and so on and so forth. At the end, you will have your best model in here with the best C value, okay, as a result of the cross validation. Also, we have scale. That's remember when we talked about SVM, you need to standardize or you need to scale the data or to have the data all on the same scale. But since we generated the data in this example to have a mean 0 standard deviation of 1, there's no need to scale it. But otherwise, it's important to scale your data. For SVM with nonlinear kernel, so that's how we use SVM most of the time. We use the kernel SVM or the kernel check in SVM, where we can choose the function in here. So the kernel type. You can still use linear. So one of the values that you can set the kernel to as a linear, which is going to be the same as the SV classifier, the linear SV classifier. You can choose polynomial where the degree, you choose the degree that you want, and if not, the default will be 3. But in this specific example, it's a radial kernel. We see in the equation for it in the slides. And with it, you have a gamma. Now we have another parameter that you need to select or tune. Besides the cost, we have gamma. And again, we can try different values for gamma and different values for cost. To tune, we can go back to the tune function. And in this tune function, we're providing different values for C that we want to try, different values for gamma that we want to try as well, and it will run tenfold cross validation with these different choices. And at the end, you will have the best model. The best model in here means the one corresponds to the best settings for those parameters. The default for SVM in the case of multi-class classification is 1 versus 1. So it will use this 1 versus 1 approach. And that's an example in here for a multi-class classification. You can go through it. And at the end, there is also an example using the data set for the gene expression data. It's one of the data sets in the library that comes with the textbook. And it's a classification problem. So given the data about patients in the gene expression data for a number of patients, and we, the prediction or the classification into what kind of cancer. So we have like 4 classes. So it's a multi-class classification. We have 4 classes, and we will make a prediction or the case classification into those 4 classes based on the gene expression data or the measurements that we have. And we have 2,308 measurements, corresponds to those number of genes. And based on that, we classify into one of 4 classes. All right. So questions? I've seen somebody raise their hand. Let's see. Go ahead.
Okay. So I've been having a lot of problems plotting the SVM with the multiple classes, and I sent an email to the TAs on Saturday and just heard back 10 minutes ago, which I didn't know what the instruction was, and then logged on this morning and we couldn't figure out why the plots aren't working. So they're plotting with the multiple classes, like all my other plots are working except that one. And you don't have an example of that on the file. And so I've tried different options and it's running and I'm not getting any errors. It's just not popping up. And I've tried loading every library that other people have offered and none of it's working.
Anybody has, we can create a thread in discussion on Canvas, and we can see if anybody has the same issue and how to resolve it. And we'll, with the TAs as well, they can basically participate in this discussion. But by my understanding in here from your question is the plot, which is basically the plot of the SVM fit, correct?
Well, it's part D for question 7. So I have the 3 fit, 1 linear, 1 radial, and 1 polynomial. And it says to plot a bunch of graphs to show your fits. And but when you have the multiple classes, none of those plots are working.
Okay. Well, I need to see what's the function in here and why it's not. So let me just hold on. Let me share. So this plot in here, so the plot of SVM fit with the data, you're saying if it's a multi-class classification problem, it will not, nothing will come out of the function, right? So it's not.
Yeah, because on the question, it gives you a different way. So if you go to question 7 over here, it says to use. It's like hint, and it says the plot parentheses SVM fit comma date dat won't work. You have to do plot parentheses SVM fit comma dat comma x1 approximate x4 parentheses, and that doesn't work. And I found this loop online, and that doesn't work either. And everything's running, like I'm not getting an error. It's not telling me it's not working. I just don't get any visual plot.
Okay, so let's discuss this offline. I don't know if TAs are listening. And when is the due date for the assignment?
It's due tomorrow, but I'm trying to, finish it so I can work on the actual project.
Okay, so let me see, because I'm not sure. Yes, go ahead.
Yeah, so I think that the TA responded to this. I don't know if you checked that.
Well, it was 10 minutes before class. And
yeah, so that may fix your issue. That's only 2 days after you posted it. So there was also a couple of comments. Check on the comments that a couple of other students also commented on there. So see if that fixes the issue. So basically,
So
make sure
what
that
does
coded is.
vectors means, because I have it so that it's 1 or -1, like the book said. So I don't understand what that means. So if we can maybe after class talk, so I don't take up class time.
Yes, yes. That will be
Okay.
better. All right.
Okay.
All right. So we will start with a new topic. Let me just share.
Oh.
All right. So neural networks and deep learning. This is gonna be. It's not. You know, the textbook that we have for the class statistical learning doesn't include neural networks or deep learning. So, so the only thing that we can provide will be those handouts, those slides. And there will be also some references that I will talk about, you know, during this class. You know, it's very important to when discussing fundamentals of data analytics and prediction, we need to mention and we need to talk about neural networks and deep learning. And to understand, you know, deep learning is basically a new term. You know, it's a kind of recently coined term, deep learning, and it's all about using or training neural networks. And in most cases, those neural networks are large, or that's the term in here, deep. So they are like large neural networks for prediction. And neural networks as a method is not new. It's actually a very old method that at some point in the 80s and 90s, they became very popular, but then their use diminished for a while until recently, where, you know, we see a lot of use in many applications, you know, based on neural networks. So they gained momentum again, and now they became very famous and very popular in many of the machine learning problems. So you know, I have a slide or two that also talk about why neural networks and deep learning are taking off recently. You know, what's the reason? You know, those methods or this method, neural networks, is taking off recently. So first of all, you know, we need to understand what is neural network, and we'll start off with an example. And this is like you know, the example in here is, you know, as you can see in this plot, in this little figure, I have a number of points, a number of data points that represents houses. We see the price in here, and the question is how we can build a model that will predict the price using the size of the house. Okay, so it's a simple house pricing prediction problem, and you know, basically we can look at those data points. And since we are kind of all familiar with linear regression, you know, it's easy to kind of make a plot in here of a line that we will use as our function to estimate the price using the input variable or the input data in here, which is the house size. So one can, you know, basically just you know, make this line in here our linear model or linear function, okay? And I'm gonna try and use a different color. Okay. So since, you know, pretty much we are all familiar with linear regression, that's, you know, basically our solution. This is our function that will predict the price using using the size of the house. Now, So it's all about coming up or estimating this function, and to put this in a different notation that we will be using for neural networks. Think of an input x that will, in this case, which is the size of the house, into a node, a processing node, where we have our function f of x, and this will produce the output y, which is in this example the price. Okay, so the function in here, this is the node, or sometimes we call it the neuron of the neural network, and that's like the simplest neural network that you can think of, is just one neuron, one node, where given an input signal x, this node or this neuron will do some processing, some transformation or some calculation, and then the output in here will be the estimated or the predicted value y, which is in this case price. The function in here, it just happened that this function is a linear function, and there's a way for us, because we learn linear regression, to estimate the coefficients for this function, the intercept and the slope. We can add to this function here to kind of make it different than just a linear regression. We can think of, since the price of a house will never be negative, then we can choose at the beginning maybe a value of 0 as a price, and then we take off at some point. So this is going to be like a different function than just a linear. So it will be 0 at the beginning, and then it will take off after that. And this is actually a very important function in the context of neural network, this function in here. Okay, so that's how it looks like. And this function, later on, we will see more details about it. It's a ReLU function. It's short for rectified linear unit. And it's basically a linear function that starts off with 0 and then take off. So it will be minimum of 0 and then greater than 0 after some point. So later on, we'll go back to this ReLU function. So this f of x inside this neuron will be a function that will transform or will process the input data and produce an output. And again, this is like a very basic and simple representation of a neural network. There is only one neuron that will do this calculation. I need to mention that neural network is not, it's a totally different algorithm. It's a different concept in here. Okay, so but then later on, we can see how we can use some of the functions that we learn about, nonlinear functions that we learn about in previous topics into this neurons, into those nodes, how we can utilize those. Okay, so if we are to use more features, besides the size of the house, if we have access to the number of bedrooms, the zip code, the wealth, and we are now to build a neural network that is not just one node. So in this case in here, we only have one neuron, and a neural network is built using or by stacking multiple neurons together. So in this case, if I have this size, so in this case, think of the input size in here with the number of bedrooms as to input into a node, okay, that maybe will produce, or that will maybe determine the family size that will live in this house that we're trying to predict the price for. Maybe the zip code in here into another node by which it will determine the school district, which is important for determining the price of the house. The wealth of, think of the wealth of the neighborhood, where the houses maybe with also in combination or the interaction with the zip code will give you maybe the school quality or the neighborhood quality. Okay, so all of this can be combined also into another node that will at the end produce the output y, which is in our case the price. So you can think of now we have multiple neurons. So we have multiple nodes or multiple neurons that will take the input and think of a function in here that will calculate or estimate an output that then will go into another layer where you also have another node or another neuron that will also combine pretty much the features that we learned in this intermediate level in here and combine those into predicting the output y. Okay. I see some people chatting. I don't know if you have any questions about this or not. So let me just go there. So again, for reference to neural networks, to the topic that I'm just talking about now, the slides will be your reference in here. And also I have a link to Coursera, machine learning and deep learning courses by which you can, go through and learn more. So this is, basically an introduction to neural networks and deep learning. So you can have more details using those links. So I think I have the link on the slides as well. If I will go to, sorry, I didn't mean to stop the share. So let me just go back and share. So you see in here I have a reference in here. Okay, if you guys can see it. So it's a reference for a Coursera course, Neural Networks and Deep Learning. You can audit this course, and of course, if you are interested in getting all the deep learning specialization in Coursera, you can go through multiple courses actually talks about neural networks and deep learning. And there's also another Coursera reference for machine learning, another course called just machine learning. So I have it also in the other slides. If you go to the notes in here as in the PowerPoint slide notes section. Okay. So this is basically a simple neural network where you will input your X. It's the features that you have, and Y, your outcome. And what's inside in here, you will determine when you set up a neural network, you will determine how many nodes and how many layers there will be, and everything will be, the neural network training will figure out what will be going on inside these layers. That's why we call them the hidden layers. So in a way, I wrote pretty much the size, for example, with the house, and the number of bedrooms will determine the family size. The zip code with the wealth maybe will determine the school district quality. So because we kind of know that the interactions of those features will produce, features that we can, basically understand. But this is not what what's going on actually in a neural network. In a neural network, the features learned at the hidden layers, the internal layers, will not be as we can determine those. It will be kind of the neural network itself will determine how to learn those intermediate features. So, and the other thing is, it's all completely connected. All of the connections in here, so it's a fully connected network. So given your x1, x2, x3, and x4, in this case, the features corresponds to a house, the features that we collected about a house, into now, you see in here, into the internal nodes, and now they are fully connected. And from there into the output layer. So this is what we call now input layer in a neural network. This is the output layer. And now the internal layer that we have in here is a hidden layer. So this is a hidden layer. And sometimes we can have multiple hidden layers. But this one is just still, where we have only just a simple neural network so far. Okay, so each input in here is connected, or each of the input will be connected to the internal nodes that we have. So it's a fully connected network. Okay. And at each node in here, remember, at each node we will have some function that will take the interaction of those all input features and calculate a new feature that will be outputted at this link in here to be input into the second node or the second neuron at the output layer. So there will be think of multiple transformations or multiple levels or layers of transforming input data into features and into intermediate features into a final predicted value. Now, basically the idea of a neural network goes back to the first model that probably was published was maybe in the early 40s, and it was the main usage of it, or the main idea came about implementing or creating an algorithm that can mimic the human brain. So that's why I'm using a different terminology in here when I talk about the nodes or the neurons, and what's happening inside is a processing of or transformation of input data coming into this node to an output signal. And again, we can use the neural network terminology, input signals and output signals that will go into another neuron, and it's all fully connected. The same way our brain, the neural network in our brain is connected as well. Okay, so we will briefly as well go into the theory behind neural networks. And I have some figures in the slides to also explain it. Okay, so this is, by stacking neurons together, we can create a neural network, and we can go into multiple layers, and hence the name deep learning. So deep learning is coming from implementing neural networks that are large or deep. It means we have multiple hidden layers. And at each phase, if you think about it, since we're doing processing at this layer in here, and then there will be another processing at this layer in here. So we're processing this information at multiple levels, or transforming the values of the features that we have learned at multiple layers or at multiple levels. Okay. There's a true or false question. Every input layer feature is interconnected with every hidden layer feature. This is true or false. So basically, if we will go back to the figure in here, we mentioned that your input, each input in here is fully connected with all the nodes and the hidden layers. Okay, so this is true. Every input layer feature is interconnected with every hidden layer feature, yes. Any questions about this simple neural network architecture? Okay, so there were some questions that I didn't see. So does each node have to be produced from two predictors, or? Well, there was at the beginning, no, not necessarily. So it's all connected, fully connected. At the beginning, I was just trying to show you that we can learn features at the intermediate level, at the hidden layer level, from the input features. But since this example, like we kind of easy for us to understand that in the case of a house size and the number of bedrooms, we can learn a feature that we can associate with a family size. The same goes for if you combine the zip code and the wealth, maybe we can learn about the school district or the quality of the schools in this neighborhood. And that's like kind of the new feature that we can learn from the original features that we're given. But in reality, what's happening is it's all fully connected, and the features that the neural network will estimate at these layers in here. So this is, can be, you can think of the case in here. So we have x1 at 2, layer 2, we would use this notation, x2, 2, and x3, 2 as, where the second number, I mean the layer. So those are like new features that we learned from after processing all the features at those 3 different nodes. And the hope in here is the neural network will learn something different or something new at each node or at each neuron. Yeah? So, part of the difficulty in opening the neural network to understand what's going on or use neural network for inference is it's hard to kind of go back and trace the main contribution of the initial features into learning the intermediate features that we have. And sometimes we can't basically, understand why those are important or not. So we'll talk about this later on. But for now, let's just focus on, how this new architecture now is going to be working for us. And then we will go into the details of how we can create a nonlinear function inside those neurons or inside those nodes. I don't know what is a structural equation modeling. So for Geoffrey, Oliver. All right. The applications of neural networks. And again, we hear about neural networks in machine learning and deep learning in machine learning a lot, especially these days, because we know they are successfully been implemented in many useful applications. And these are just to show some of the examples where neural networks are kind of the dominant method for using or for making a prediction or for data analysis. So in real estate, as the example in here, to predict the price of a house using features that we can collect. So that's the kind of a standard application for neural networks. Applications also in online advertising, where given user information, it will predict whether you will click on an ad or not. So it's a classification problem that many companies use for online advertising. So you're not going to be, pretty much the ads that you see when you go on your Facebook or when you go on Amazon or when you go anywhere for shopping, there will be a prompt where you have an ad, and most likely you will click on this ad. So you will not see ads that you are not interested in. So that's basically using user information to predict if you are most likely to click on an ad or not. And this is, we can use standard neural network for this application. And the same thing goes for real estate. So real estate, online advertising, we can use what we call a standard and, a standard neural network. For image analysis in computer vision, where we see that pretty much the most popular method in image analysis is neural network. And the specific type of neural network that we use for image analysis is what we call convolutional neural network, short CNN. Okay, so CNN is the convolutional neural network, the most commonly used in image analysis and image classification. Audio and text. So for audio and for text. So for speech recognition and for machine translation, we use a different kind of neural network. We call it recurrent neural network. So these are the three most commonly used, or the most types, or the main types, of neural networks. The standard neural network, pretty much similar to the plot that I drew just in the previous slide. It's a standard neural network. And we also have the convolutional neural network, mainly used or most successfully used in image analysis and computer vision. Recurrent neural network are mostly or more commonly used and successfully used in audio and pretty much in signal. If you have a signal or a sequence, a time series where the order of input is important. If there is a temporal component to the data that is coming to you, like an audio. So audio is like data that comes at different time points. Or if you think of a text, a sentence, where each word is in this sentence, the position of each word is important. So that's a sequence. We process these information or these data in a different kind of neural networks we call recurrent neural network. And if we have a more complex application, like in autonomous driving, where we have a mixture of data, image, and radar information, then in these kind of applications, we can have a hybrid. We can combine convolutional neural network with recurrent neural network to have like a hybrid deep learning method. Okay, so in the context of deep learning, you will always hear about and you will learn about these three different kinds of neural networks, and that's pretty much in the next slide. This is how we drew each type, or if you go into any textbook or if you read any article that talks about neural network types, you will see these plots to represent those three different kinds of neural networks. So the standard neural network that is best used in structured data, and convolutional neural network that is best used in image analysis and computer vision, and recurrent neural network that is used in sequence analysis or time series analysis as well. Okay, so these are the three main types of neural network. We will be basically talking about standard neural network in our class, and again, it will be just an introduction to the standard neural network. You probably need a separate course to talk about all deep learning and to go into the details of the different architectures and the different ways in which you can use all these methods. So for our course here, we will just be talking about the standard neural network, and we will use it in an application where we have structured data. Okay, so the data types in here, the structured data is pretty much all the kind of data that we dealt with so far they are all examples of a structured data, where you have basically a table of features and values, well-defined values for those features, and then you have an outcome value or a column that represents the outcome that we are trying to model in here, or trying to build a function to predict. Unstructured data, that's where machine learning using a neural network is gaining a lot of success. Is unstructured data. So that's unstructured data, that's images, audio, text, all examples of unstructured data. And for those kind of applications, deep learning is the way to go. That's where deep learning is very much successful, and that's why it's becoming very famous, and that's why everybody is hearing about deep learning, is because of the success in these applications that are difficult to work if you are only using the traditional statistical learning methods that we covered in previous classes. So for unstructured data, you just don't think too much, just go for deep learning, and we can basically use CNN or RNN to process these kinds. And even the standard neural network can also help in some of these tasks. Also, for structured data, the standard neural network is is mainly used in structured data. Okay. Any questions so far? All right, thank you, Dr. Yamal. Okay, so why is deep learning taking off? Why recently deep learning is the talk of all machine learning, or people interested in machine learning. And if you remember at the beginning, I mentioned that pretty much neural network were very popular in the 80s and 90s, but then as an idea, but then nobody was using it until recently, until pretty much I would say the last 5, maybe more than 5 years. Deep learning is becoming very popular. This basically, the reason behind that is basically goes into the data, the amount of data that we are accumulating every day. If I am to make a plot of the performance of any learning algorithm, all the learning algorithms that you can think of, as a function of how much data we have, you can think of the traditional statistical learning algorithm, where the more data, so it all starts off, the same point in here, where the more data you have at this point in here, it will improve the performance. Of course, I mean, the more data, the more input data, the bigger the training sample size that you have, it will enhance or improve the performance of your training algorithm. So up to the point where in traditional statistical learning algorithms, it will flatten. So you will not, and you will not see any improvement even when you have more and more labeled data in your position. But for deep learning, in here we're trying to make a distinction between small, medium, and large neural network. And the size in here is determined by how many nodes or how many neurons and how many layers you can have in your neural network. So the more data that you can collect or that you can use in your learning model, the more the performance in here will increase. So what gave rise to deep learning is how much data we are generating every day. The term big data, now everybody's, I'm sure you all heard of big data. So data is big. We can utilize large neural network to give us a better performance with the the large volumes of data that we have or we can access. So scale basically drives deep learning progress. The scale in here and the data, the amount of data that we can have and we can access. The computation, now the computation in terms of the processing power in here and memory, high performance computing, clusters and GPUs, we can perform and we can run a very large and very deep neural network on a server, and that was impossible in the 80s and 90s. I mean, if you think at the beginning, where neural network was like kind of a new algorithm that tries to mimic the human brain, it wasn't very useful because we don't have access to a lot of data and we don't have enough computational power to run a simulation where you have thousands of nodes or neurons that are all interconnected in multiple layers or multiple levels. So the computation, the gave rise, or the performance now gave rise to deep learning. The advancement in computation gave rise to deep learning, and algorithms in general in here. Algorithms in training the neural network and algorithms in estimating the weights or the coefficients of this method. From different variations of gradient descent, and we will talk about gradient descent later, maybe in next class, by which we can use this algorithm to estimate the coefficients of the neural network, or the weights, we call them, of the neural network. All right. So when you are thinking of using neural network, think of how much data you have and how complex your problem is. I would always tell anybody who asks me when to use neural network, the simple answer is when you have a complex big problem. And the big problem in here, or how do we define, or when we can tell that the problem is big and complex, is by looking at two things: the number of features and the number of observations. So if you have a large number of features, and we're talking about hundreds and thousands of features, and when you have a big data set, and your problem, whether it's a classification or regression, then I would recommend using neural network. That's again if you have a structured data. If your data, if you're working with images, natural language, to do natural language processing, text or audio, then I would recommend neural network, of course, because traditional statistical learning methods cannot handle these kinds of data. But for structured data, if I will go back to this figure in here, pretty much, for small data set, if I will just take this section in here, where we have a small data set, then the performance of neural network is comparable to traditional statistical learning algorithms. And in many cases, actually, the traditional algorithms can beat neural network. So when you have a small data set with a relatively small number of features, there is no need to use neural network. You can just, I mean, you can still try, you can, of course, I mean, it's one of the tools in your toolbox. You can try SVM, you can try logistic regression, and you can try a small, shallow neural network with maybe just one hidden layer, and a small number of neurons. And maybe the performance of this neural network will be, similar to SVM and logistic regression. In some cases, maybe not. So that's the case when you have a small data set. So where neural network will have a similar behavior to traditional neural network. And if we go to the section where we have big data, that's where we have big data, and with big data, you use neural network. Okay. So where we see, and again, this is based on the practice in in machine learning. The general practice, it was based on people reporting their results when using neural networks on big data problems. The performance will be much better than traditional learning algorithms. And again, this goes for only structured data, because the case with unstructured data, we may not be able to use the traditional learning algorithms to do image classification or to handle text data. Okay. So you need a nonlinear big problem, whether it's a classification or regression, where neural network can outperform or can give you good performance. So talking about unstructured data, and to show you how neural networks can efficiently handle problems like problems in computer vision, like an image classification or a car detection. In this example, a car detection algorithm, as an example of unstructured data. So for us, as humans, it's easy to kind of see this image and recognize, what does this image represent? But when we all can see this car in this plot, in this slide, the computer doesn't see it this way. The computer will see the representation of this image as a matrix of pixel intensity values. So if we will just zoom into the door handle of the car, so the camera in here will come up with this representation of pixel intensity values. And these values range from 0 to 255. That represents the intensity and the brightness of the pixels in this image. So the values in here, again, from 0 to 255, where 0 is the black, 255 is white. So it will be all the values between this range will be, the different variations of the different shades between black and white. And that's only for grayscale. So that's a grayscale pixel intensity values if we think of just black, white images. And so basically, if we, for us, again, as humans, we can easily recognize this image, but for a machine, it's going to be a matrix of values, a matrix of pixel intensity values. And now we need to come up with an algorithm that can take this matrix and be able to recognize that this matrix of values corresponds or represents a door handle in a car. Okay, so that's a complex problem. That's not an easy thing to program. Okay, and that's only the case in here with only grayscale. And if you want to introduce colors, then you need to have a matrix now for the blue green. If I will just the basic blue green red representation of an image, then you will have a matrix the same size in here. And again, the size of the matrix depends on the quality of the image itself, or the image dimension. So you need now pixel intensity values for the blue color, and pixel intensity values for green, and the same thing for red. So you'll have 3 matrices to represent the image. And that's a lot of features. That's thousands of features. Okay, so if you will think of, if we will take an image that is only 50 by 50. Okay, so 50 by 50 pixel image. That's just like an icon, like a small image. Then, if we are talking about grayscale, then that's 2,500 pixel intensity values. And if we are talking about red, green, blue, that's you need to multiply this by 3. So 7,500 features to represent a 50 by 50 pixel image. Okay. Usually, images 50 by 50 is just a really, low quality, very small picture. So usually it's in hundreds. The dimension will be, and sometimes thousands by thousands. So the case in here is you have thousands now of features to represent an image, and if it's in colors, then you need to multiply by the number of dimensions used for those colors. And this is going to be your input to the learning algorithm, by which the output will be a classification if this is a car or not. If we'll just use this example as a car detection, giving all these values that we input, I want the algorithm to give me a yes or no, as a car or not a car. Okay. So in a car detection, we build a neural network. We train the neural network on a number of input samples of cars, labeled data. So, so we input those images, and of course we will, transform each image into its pixel intensities, pixel intensity matrices, and with the label that this is a car, and a bunch of other images that are not car, and train this neural network to, using these input samples. And when it comes to testing, we give it a new image, and the neural network can tell us if this is a car or not. Okay. So that's basically just a representation of what I just said, where your input samples will be labeled samples of cars, and can represent those as the plus, the positive class, and we have the negative class. And if we are only using like just 2D, 2 pixels, then the learning algorithm should be able to kind of come up with this function that will distinguish between the pluses and the minuses, the positive class and the negative class. If we are to use just 2 pixels, but in reality we have thousands, the number of pixels in here in terms of thousands, and that's a very large feature, or high dimensional problem in terms of the number of features. So these kind of problems that are best suited for deep learning and neural network, when you have thousands of features and when you have a large data set that you can use for training, especially if the problem uses unstructured data. So that's basically deep learning. In most of the applications for dealing with unstructured data are based on neural network. So the algorithm goes back to to try and mimic. So the origin of the algorithm is to pretty much try to implement or create a machine that can think and learn the same way we learn as human. So the algorithm in here is to mimic the brain, and hence the terminology and hence the name neural networks, right? So, and sometimes, to distinguish, we say it's an artificial neural network, because we know that the brain is a highly complex, nonlinear, and massively parallel network of neurons. So can we write a program? Can we create a program that can learn the same way the human brain learn? From examples, of course. I mean, in the context of supervised learning. So given input data and labeled data where we know the outcome, can we create this program that will do, or that will behave in a way the same human brain is functioning, to be able to recognize and distinguish and classify the objects or the different objects given to it. Okay. So the theory in here is the one learning algorithm hypothesis, and also this goes to the back to the days where machine learning and neural network was the talk of all scientists who are interested in creating a machine that can have an intelligence the same way humans are intelligent. So there's also, I provided some references for the one learning algorithm hypothesis that computer scientists use to create neural networks, or to implement neural networks and work on neural networks. So the hypothesis goes into explaining that we don't have multiple learning algorithms, and our brain is just one learning algorithm. So for the parts that process your, that can understand or recognize. So from, when you see an object, this is the part in the brain that can recognize this object, and this is the part in the brain that can hear and understand hearing. So when I'm talking to you, you understand what I'm saying. So this is the part that is responsible for processing those signals or those waves. So if we cut the wires that connects your ears into this part of the brain, the neurons, the connections, and we rewire the optic nerves coming from your eyes, then this part will learn to see. So the part that was trained to hear and understand hearing will now be able to learn to see. So in other words, we don't need a different algorithm or a different function to train this part in the brain to understand a different something different than the original thing that was trained on. The same goes for other functions in different areas in the brain. If we do these rewiring, we can train this new part to understand something else. So this is the hypothesis in here, the one learning algorithm hypothesis, that your brain is the algorithm that controls how your brain function is just one algorithm. And these are the references if you want to go into details. Okay, so into the details of this hypothesis. Okay. So this is how this is how a neuron look like in the brain. We have the neuron, the cell body, and we have the dendrite, the input wires that that moves the signals, the input signals into the body of the cell, the neuron, where there will be some processing done inside the neuron, and the output in here will be carried out on this output wire, the axon. And the output wire is connected with input wires from nearby neurons and so on. So they will form a network. So this is, another so we see in here how one neuron is connected with other neurons. So now the output wire in here, the axon of this neuron, is connected with the input wires of nearby neurons and so on. So they are all interconnected. And now the thing in here is the input signals, we'll go back to this one. So the input coming to those dendrite, to those input wires, as signals, as with different weights or with different different kinds of signals, and the processing in here inside this neuron will produce an output of a signal with a different strength. So that's what I'm trying to say in it. The input will have different strengths. The signal processing will transform these inputs and will produce a signal that will go with also a specific strength for the signal. So these are the bases of artificial neural network, is basically to think of a transformation in here. So they think of, again, going back to the representation that we showed at the beginning, this is going to be my neuron. This is the body, the cell body, where the transformation is done. And we have input signals, so X1, X2, X3. Let's assume we only have 3 input data or input coming, and that's the direction of the input coming into this neuron. And with each input, we have different signal strength. Okay? So W1, W2, and W3 are weights, what we call them weights in the terminology of neural network. And the weight in here is, think of it as the strength of the signal coming from the input features that we have. Some function in here will go into transforming the input signals multiplied by their weights, or the weighted signals. And then you will have your output, which is going to be, on the output signal, which is going to be the predicted value, right? So in a way, this is a neuron, just one neuron, and to build a network, you need to stack multiple neurons together, and we can have them in multiple layers as well. Any questions so far? Just going through the terminology of neural network. So this is the first artificial neuron model that was introduced in 1943. As you can see, we have our input features into this neuron in the middle, V. Okay. So, and we also have, remember, we have different weights to represent, or to basically to represent how the strength of the input coming from the different input features that we have, or the input nodes. In the initial model that was proposed in the 40s, the neuron itself, the processing done in the neuron is basically just a summation of the inputs multiplied by their weights. So you just, you take X1 multiplied by W1 plus X2 multiplied by W2. So you sum the inputs multiplied by their weights, and you choose a threshold value, and the input signals in the initial model, the input signals were either positive or negative, okay, and the output will be positive or negative. So you take the summation in the node, the neuron, and then you apply a threshold function. So if the summation is greater than this threshold, then you output positive signal, else your output will be a negative signal. So that's again, the initial model when scientists start to think of an algorithm to mimic the neural networks in the human brain. They thought of it as input of negative, positive signals with different strengths that we can represent with weights in this figure in here. The neuron will take a summation, and then we apply a threshold, and this threshold will determine if the output will be positive or negative. So the set of connections, we call them, they are called synapses, and they're interlinked to create a network. Each synapse has a weight that represents the strength of the connection. The neuron body in here will will do the calculations and apply the threshold function. So, and this is also important in your terminology, the activation function. Okay, so the activation function here is the one that will produce or will determine the output to be positive or negative. And in this case, this activation function is simply this threshold comparison. So that's our activation function. So after the summation in here, we apply this activation function. It's another representation where we have multiple input now, more than just two, with the weights, and that's the summation unit. Basically they are, they should be, I should have this, written inside just one unit. Okay, just, so it's all in one. That's the neuron inside. So you do the summation first, and then you apply the activation function. Now the activation function can be just a very simple threshold function, but then we have other choices. We can choose this activation function to be a linear or nonlinear, and we will see what's available for us. Okay. I think we only have 2 or 3 minutes, so let me see if anybody has a question. There is an error in slide 20. Let me go to slide 20. Okay, Lucy, what's the error? You can unmute yourself. Yes.
Okay. Hi. Can you hear me?
Yes.
Okay. So this is really technical, but for some reason it's been bothering me for a while. Okay. For neurons in the brain, it shouldn't be a Schwann cell. It should be a cell called the oligodendrocyte. Schwann cells are protections, the layers of protection for neurons outside of the brain and the spinal cord. They're for everywhere else in the body. But for specifically neurons in the brain and the spinal cord, it should be something called oligodendrocytes.
Okay. All right. So can you fix the slide for us and send it?
I don't know how to Photoshop. I'm sorry.
Okay. All right. I'll fix it myself. So we'll fix this slide. Okay. But then again, it's pretty much in terms of the idea behind the neural network is in a way to mimic the functions of, and again, like sometimes we use some terminology in here that is from the brain neural network, and we change some of the other terms to a more computer science terminology.
Yeah, I understand the correlation and the analogy. It's just This is, in case anyone is going into neuroscience or something in the future, this is something that is pretty important, actually.
Okay, thank you so much. Appreciate it.
Thank you.
Any other questions? Any questions about the project? I mean, we can later on. I don't think we have time. We only have 1 minute. But you know, if you have any questions, you can also, you know, create a thread on the discussion on Canvas, and let's get everybody involved in discussion as well. You know, it's a really nice thing to because again, in the project you can discuss details, but every team should have their own solution at the end, their own implementation of the project at the end. And the same goes for, you know, any discussion that you want to have for the homework. You can also start the discussion over there and let everybody participate. All right. So that's it for us today. We will continue next time with neural network, and then we'll have probably 2 classes actually to talk about neural network, and then we will be left with unsupervised learning. So far everything is supervised learning. So guys, please stay safe, stay home, and we will see you next time.